Hi students. So in the last lecture we were discussing the what is the role of the virtual memory, what is the need of virtual memory, why we required the concept of virtual memory in today's computer. Along with this we have discussed that how a virtual memory will perform its function, how the illusion of large memory can be created with the help of virtual memory although the computer is having less primary memory, how the large programs or multiple programs can be executed through the virtual memory. As it was discussed that the large programs or multiple program will be divided into different frames or different pages, then on the basis of need as and when the particular page is required. So today we will discuss how can we create the physical addresses from the logical address. So the today's topic will be how to access the page table from the memory, means how can we convert the logical address into physical address for any virtual memory. So as we have already discussed that the virtual memory will be having one logical address which will be generated by the CPU, and that particular logical address will be having two parts. One is called the offset, another is called the page index. How many bits will be reserved in the page index, that will depend upon how many pages are there in the page table. So number of pages in the page table, or to define the address of each and every page of the table, the number of bits will be there in the page index, and where the offset will be used to indicate the or used to identify the required location within the page in the main memory. So as we can see that the number of bits which will be there in the page index is coming from the logical address, and these number of bits will depend upon how many pages are there. So here we are considering one example in which we have considered that we are having 4 pages in the page table, and on the other hand we are having the 8 frames in the main memory. So with the help of this particular simple example, we will try to understand how a logical address can be converted into physical address. Okay, the typical size of the page or typical size of the frame is considered to be having a range of 4 KB to 64 KB, but if for this particular example we will consider that the typical size of the page is 4 KB. So as the typical size of the one page is 4 KB, and the same size will be used to define the one frame. So that is why the offset of this particular example will be 12 bit. So 2 raised to power 12 will be equal to 4K. So that is why the 12 bits will be reserved for the offset to define the offset of logical address, and same number of bits will be there in the physical address as well, because the size of the one page will remain same with the size of the one frame. Here we have considered that the 4 pages are there in the page table. So that is why the number of bits which will be required to define the page index will be 2 bits. So the total number of bits which are required for the logical address, and whatsoever the address will be generated by the CPU will be called as logical address, will be having total 14 bits. So 14 bit logical address will be there for this particular example, which will be having 4 pages along with the page size of 4 kilobyte. If the size of the page will change, then accordingly number of offset will be changed, number of bits required to define the offset will change, and if number of pages will be changed, then the number of bits required to define page index will also be changed. Okay, so now we will move how can we convert this. As we can see that the CPU is generating the logical address. One part is page index, which used to define the page in the page table. Once the whatsoever the address will be there in the by the page index bits, that particular page will be selected. Let's suppose in this particular example we are going to select page 1, and in page 1 it will define the one frame, and what will be the address of that particular frame, that will depend upon what is the address of the frame. So if this is the address of the frame, so accordingly the address will be stored over here. So here in this case we want to assign the frame, or we are having the frame number of frames in the main memory are 8. So that is why the 3 bits are required to assign the frame number to each and frame address to each and every frame of the main memory. So for the page frame index, the 3 bits are required, and offset will again be similar. It will be 12 bit. Okay. So by using this particular method, we can convert a logical address into physical address. This was a very simple example. Now we will try to understand with the help of another example. How can we calculate the physical address and logical address? We will go with one example. So let's suppose this is a one example in which we are having one logical address size that is equal to 4 GB, and physical address size is 64 MB. So meaning of this is the size of our main memory will be 64 MB. So total number of combinations, the total number of frames will be 64 MB, and page size will be 4 KB. We'll have to calculate what? Calculate the number of pages. Number of pages will be how many number of pages are required in the page table, number of frame and size of the frame. We'll have to calculate it. Then size of the logical address and size of the physical address. So we will try to calculate it. So this is the solution. So as it is given, the logical address size is 4 GB. So if logical address size is 4 GB, so we know that how can we calculate the size? The size of any memory capacity will be calculated on the basis of this equation. 2 raised to power m is equal to n, where n will be the number of combinations, that is equal to 4 GB, and 2m will be the number of lines, number of bits are required to calculate the value of n. So here by using this we will have to calculate the value of m, and n value is given, logical address size which is 4 GB is given. So what will be the value of m, or number of bits which are required for LA? That will be 2 raised to power 32 will be equal to 4 GB. So 2 raised to power 32 will be equal to 4 GB. So number of bits which are required to design a logical address for a 4 GB virtual memory, that will be 32 bits. Okay, so total 32 bits, 32 bit long logical address will be generated to address the each and every location of 4 GB, 4 gigabytes. Okay, so as we know that whatsoever the logical address will be there, that will be divided in two parts. One is called offset, another is called page index. So till now we have calculated the logical address, number of bits required for the logical address, that is 32 bits. So out of which some bits are reserved for the offset. So as given in the problem, the page size is 4 KB. So size of the one page is 4 KB. So first of all we will calculate how many bits are required to how many bits are required to assign the page size of 4 KB. So given page size is 4 KB, so number of bits required for the offset will be 12 bits. So again we will use the same principle, 2 raised to power m is equal to n. Here n is 4 KB, number of combinations of the page will be 4 KB, one page will be having 4 kilobytes. So to assign the address to each and every byte of 4 KB, we require the 12 bits. So 2 raised to power 12 will be equal to 4 KB. Okay, so out of 32 bits which was totally reserved for the logical address, 12 will be reserved for what? Offset. And what about rest 20 bits will be used for the page index. So the number of bits required for page index will be 32 minus 12, that is 20 bits. So 20 bits will be used to define the use as page index. So if we'll have to calculate the how many pages will be there, so number of pages can be calculated. 2 raised to power 20 is equal to 1 mega. So 1 mega number of pages will be there, and the size of each and every page will be 4 KB. Okay, so this is how can we calculate the number of pages, and how can we calculate the logical number of bits required for the logical address, okay, or size of logical address. Now the second thing was given, that is PAS, that is physical address size, and physical address size was given 64 MB, means we are having a memory whose size is 64 MB. So as we know that the 64 MB size is there, so out of which the 4 KB is reserved for the frame size. So first of all, we will try to calculate the total number of bits, how many bits are required for physical address of 64 MB. For 64 MB, 26 bits are required by using the again same equation or same formula. So 26 bits are reserved for physical address. So out of which, as we know that the page size was 12 bits, so similarly frame size will also be 12 bits. So 12 bits will be reserved for the offset. So 12 bit will be offset, so rest of the bits will be used for the page frame index. So total number of bits for the physical address was 26, out of which 12 we are using for to define the frame size. Frame size means 12 bits will be used to define the frame size, and the rest 14 will be used to define the page frame index. So what will be the, how many frames will be there, what will be the number of the frames, that will be 2 raised to power 14 is equal to 16K. Okay, so nutshell, what can we can conclude from this, as in this particular example we are having a virtual memory is 4 GB. It looks like we are having 4 GB virtual memory, but in actual the main memory is of only 64 MB. So by using the 64 MB, we can execute the programs which are stored there in the 4 GB, and this is possible because of the concept of virtual memory. So it is giving the illusion to the programmer that I'm having 4 GB memory with my CPU, but actually the only 64 GB is there for the program to execute. So this is the concept of virtual memory, which is very important to increase the execution speed of the today's processor or today's computer by using the less main memory, so which will reduce the overall cost of the computer as well. So this was how can we calculate the physical address and logical address. So here we can see this. So the number of bits which are required for the logical address are 32 bit, out of which 12 bits will be reserved for offset, because the page size is 4K. If page size will be 8K or any other, then accordingly number of bits will be changed, number of bits for the offset will change, and rest of the bits, 32 minus 12, rest of the 20 bits will be used for the page indexing. Okay, so how many pages will be there? 2 raised to power 20. 2 raised to power 20 pages will be there, and that will be 1 mega. Okay, so as we have already calculated that the physical addresses, to design the physical address for this particular example, 26 bits are required, and out of which 12 will be used as offset, and rest 14 will be used to define the frame. So if we will use the 14 bits to define the number of frames, then number of frames will be 2 raised to power 14, that will be equal to 16. Okay, so this is all about this particular example. So I hope you will be able to understand how can we calculate the physical address from the given logical address or even given capacity. Okay, so next, in the last class we have already discussed that what will happen if whatsoever the frame processor want to access will not be available in the page table. So that particular problem is called page fault. So how can we handle, or how the CPU will handle the page fault? Okay, so as we know that the page fault condition will occur whenever CPU will send a logical address, and out of that particular logical address, whatsoever the address assigned to the particular page, and if that particular page is not having the frame address within the that particular frame, and as we have already discussed, that will be defined with the help of invalid, or by putting this particular bit is equal to 0. If this bit is equal to 0, it means this particular frame number is not available. It is not available. Okay, so what type of different steps which are required to handle this type of situation, how the computer will be able to get the required frame or required data from the main disk. Okay, whenever this situation will occur, whenever this page table will indicate that, and processor will come to know that the required page is not available and it is showing as invalid, at the same time processor will generate a trap, and where trap is a interrupt, and through that trap or through that interrupt, processor will activate the operating system. So operating system will come into action, and as soon as the operating system will come into action, before the control will be handled to the operating system, the processor will save the user mode register and exit from the user mode. Okay, so once it will exit from the user mode and operating system will take the control, then the operating system will check either that interrupt was for the page fault. So many more interrupts will be there for the operating system. So first of all, the role of the operating system is to detect either the existing interrupt is due to the page fault or not. Once it will confirm that yes, it is due to the page fault, then what it will do, then operating system will send the page number, whatsoever the information was available on the page number, to the main hard disk, or to the secondary memory. And it will, before it will send to the secondary memory, it will check the page reference and location of the page on the disk. So it will confirm or it will verify the required information for the location of the disk. Okay, so it will verify the page number, page reference and location of the page on the disk. Issue a read from the disk to a free frame. So what it will do, it will issue the read control signal to the disk, and once the disk will receive the read signal, then it will send the required data to the free frame within the physical memory or within the primary memory. If the any space will not be free in this, then first of all processor will have to shift the already used frame to the disk and then will create the free frame. If free frame will be there, then automatically it will read the data from the hard disk and store to the required information be stored to the available free frame into the physical memory. Okay, it will take some time as the operating system will have to read the data from the external hard disk. As we know that the speed of the hard disk is very slow, so it will take some time, mostly in millisecond, to read the data. So meanwhile, what CPU will do, the CPU will allocate the control to the another user during this period, so CPU can perform some another task during this period. Once it will receive an interrupt from the disk that your read operation is completed, your data have been written into the required free space, then what it will do, it will correct the page table and other table to show the page is now in the memory. So what it will do, once the data will move from the hard disk to the free slot available for the frame, and once the data will be read, then the signal will go to the page table which will contain the address of the frame table. So it will reset the page table and will fill the frame number at which the new information have been stored, and at the same time this invalid bit will be changed to the valid bit by putting it is equal to 1. So once this bit will be equal to 1, once this bit will become 1, immediately after the data of this processor will come to know that now the required whatsoever the information it will have to read is available in the physical memories, and accordingly it will restore the user registers, processor state and new page table, and then resume the interrupted instruction. So whatsoever the instruction was data required for the that particular instruction, that will be restored. So this is all about how we can handle the page fault. Okay, so this is all about today's lecture. Thank you.